So this week we're going to talk about the mid-latitudes weather. In other words, where we live, what our weather systems are like. So what shapes these weather systems? We talked about the global climate before. Now let's just take a quick peek at air masses. There are lots of different kinds of air masses. Air masses are just a large mass of air, large area of air that has the same characteristics. So think about it. They're going to form over areas that have similar characteristics. And last time we learned about some areas that have high pressure systems that like to sit over them. Along 30 degrees north, for example, there's typically a high pressure system. Well, what's going to be along that high pressure system? Well, think about it. It's over the open ocean, fairly tropical. So you're going to get maritime tropical air masses. These air masses are going to tend to be moist. They're going to tend to be warm. Now, the same token, that air mass in the summertime, maybe the desert Southwest might form a continental tropical air mass. It's fairly dry, fairly hot. You know, when you're going to get the 100-degree weather out in the Midwest. We also have continental polar air masses or Arctic air masses. There are even maritime polar air masses that form over the upper northern part of the oceans, where they're fairly moist, but cool. They're not ridiculously cold, we'll say. So if you were to look right now, for example, you would find a continental polar air mass is forming, developing over Canada right now, kind of inching into the U.S. a little bit. Temperatures are generally in the teens, even below zero in some places up here, and 20s, and the dew points are all in the teens or single digits. So it is a continental polar air mass. Nice high, 1021 high with it. And then here's your boundary of that air mass, a cold front. And it's a boundary on both sides. It's stationary because of the Rocky Mountains out here blocking it, but then it's moving east right here. So that is an example of a continental polar air mass. And the boundaries between air masses are where you find up with fronts. So one thing to think about too on air masses, think about a hot air mass and moist traveling over land. Well, if it's over bare ground, it's still going to stay fairly warm. It just might not have as much moisture with it. But we already know that air masses that develop over Canada, where there's a lot of snow cover in the wintertime, when they move over the bare ground, they modify very quickly. So continental polar air masses are going to modify much faster than maritime air masses or tropical air masses. Stationary front. So with that, let's take a look at a stationary front right now. As a matter of fact, if you look at the current weather map, we have a stationary front right across the southern Tennessee border, the Carolinas. It's not moving at all. To the south of that is very much of a maritime tropical air mass. To the north is remnants of a continental polar air mass. So there's a contrast of air masses again between the two. So if we continue on with this, also remember warm air always is rising up over cold air. Remember, warm air is lighter. So on a stationary boundary like that, the warm air, the clouds are going to tend to be the north of the boundary, while the south of the boundary is going to have more sun. Now, right along the immediate front, maybe a lot of thunderstorms. If you have a warm front, you have the same thing, except the front is moving. A warm front just means warm air is taking over. If when a front passes you, the air is warmer and typically more humid than was before it passed you, it's a warm front. If it passes you when it gets colder, it's a cold front. And a cold front is pretty steep. Remember, they have lots of more density to the air, so they're fairly steep. You tend to get more thunderstorms with cold fronts. And cold fronts can come in different directions. Now there's something called an occluded front. Occluded fronts are kind of forming at the last end of a cyclone's development. What happens is the cold front overtakes the warm front. It pushes it up so fast, the cold front has moved that warm air, and it winds up the warm air is all aloft over top of it, the real warm air. So it actually pushed that air aloft. Now, there's two types of occluded front. One's a cold type occlusion, where the coldest air is to the west of the front, and warmer, slightly warmer air, but cool air nevertheless ahead of it. And the other one, typically in the maritime northwest, or whatever you might find this, where you have a cool air mass and a cold air mass farther east. This is the Norwegian cyclone model. It's the basis. It was developed a long time ago, but it's a really good basis for how a cyclone develops. What you wind up with in the incipient stage is you have one of your jet streams coming down, and remember, left front quadrant or right rear quadrant of a jet have a divergence aloft. Well, this is in the left front quadrant of that jet. So you have divergence, and it's along a cold front or a warm front. Typically, you'll begin to develop a warm front along them. So you're developing a temperature contrast. You're getting phonogenesis in here. As it develops, pressure begins to drop. Winds begin to blow more around it. You're pulling air into it, and you develop a comma head, literally on the satellite image. It looks like a comma head. And it really strong ones, you get the occluded front with them. Notice how the occluded front is right near the actual low pressure, and it's very close to the low pressure aloft. So the temperatures in the low, actually aloft, is more intense than the low at the surface many times. And eventually, sometimes you get a triple point out here where you have an occlusion, a warm front, cold front, and many times a neutral low may form right along that triple point and move out. Another aspect, way of looking at cyclones or extratropical cyclones is to look at conveyor belts. Well, we want warm, moist air to come up into it. So you have the warm conveyor belt coming out of the tropics typically. Sometimes if you have the low coming up in the Midwest, that warm conveyor belt might originate in the Caribbean Sea. It might originate in the Gulf of Mexico. Then you have the dry air mass coming out from the northwest, getting pulled into it. Part of it comes down, wrapping around. But you also have the cold conveyor belt. The cold conveyor belt is actually what forms the comma head that you see in these clouds. What happens is the cold air is being pushed upwards and rising ahead of the warm front. When it's rising, it's already cool, it's moist, so it's forming clouds in the lower layers. And when it hits the jet stream, it begins to turn. It turns anticyclonically to follow the jet. So you wind up getting a comma head. So the cold conveyor belt is what actually forms your comma heads. Now, cyclones have all different kind of weather depending on what quadrant you're in. And in the summertime, obviously, you're not going to get snow, but you may get rain to the northwest of the cyclone, or you may get snow in the wintertime, more rain ahead of the warm front. But when you get in on the other side of the warm front, you're going to get more showers and thunderstorms. So actually tracking where these lows develop and form and where they move to can make a big difference in the kind of weather you're going to get. If I told you the low was going to come up over Pittsburgh, your weather in Ohio might be more of a snowstorm. If I told you that same low was going to come up across Toledo, well, Ohio might actually have some ice or snow initially, but then change to all rain, and eventually might even have some thunderstorms as the low moves by with the cold front. And remember, because of the cold air, pressure drops faster in the vertical, so you wind up with the most intense cold core cyclones are aloft. And they'll typically be back to the northwest of the low. Warm core cyclones, and they're not just without any, they all have no fronts, but they're not always all stationary. There are some, like tropical storms, that are warm core cyclones, but most of them are. They form a thermal low. Happens in the summertime over the desert southwest, and you see these low pressure systems, but you actually have an anticyclone aloft. And you get the Arctic cold core anticyclones Warm core. Lake breezes. Think about it. If you have warmth developing over land, you're going to tend to get a little bit of air lifting, convection there. Going to pull the air in, help it to rise. It just makes a circulation. In the nighttime, warmer ocean water, maybe the breeze will go that way instead. So you get the sea breezes and land breezes, and we've talked about how they can lead to showers and thunderstorms developing. Valley breezes are just nothing but the bare valley walls heating up. So the air begins to lift there, sinks in down over the main valley floor, bringing cooler and denser air into it. Mountain breezes are at night. The cold air on the slopes flows down, rises in the valley. Chinook winds. They can happen in the Rocky Mountains. Many of you probably don't remember back in Olympics occurred in Calgary. They could never get enough snow because the Chinook winds were occurring at a steady pace and eating up the snow. They're called snow eaters because you think about it, they come down the mountain, they warm as they descend. They also get drier as they descend. And one of the famous Chinook winds that many people hear about is the Santa Ana wind. The gravity initiates the downslope flow, drops down off the mountains. It can flow really fast wind, warms, adiabatic compression, and you wind up very, very dry with literally humidities less than 5% in some cases. Hubbobs are just dust storms. They generated through a thunderstorm downdraft. They can occur over the desert southwest in the U.S. or any other desert. The Sahara has them as well. What happens is the rain gets evaporated as it's coming down, and you wind up with cooling, counteracting the warm compression that's going down, and you wind up just a lot of cold air hitting the ground, blows up the dust, and you create these fabulous dust storms. Heat bursts occur from convection where the rain never reaches the ground. They occur in the Midwest. I actually experienced one in Oklahoma City once, where the temperatures were in the 70s before the thunderstorm came through. We never got a bit of rain out of that thunderstorm, but the temperature rose into the mid-90s due to the compressional heating of that air coming down in the thunderstorm. So the last thing I wanted to show you was just see if we can look quickly. There's a low that we just saw out here. This is today's weather map. Look at this low, cold front. By tomorrow, that low is pretty intense, pretty strong cold front along it. And the next day, the low's out over north of Nova Scotia, and it's occluded front with it. So if you were to look at that just today, here's the jet stream for tomorrow afternoon. Low up here somewhere, probably right, at the head of the left front quadrant. And guess what? The model forecast says it's going to be right there. Oh yeah, you can see all the warm moisture coming up out of the Gulf of Mexico out ahead of it. Cold air coming down behind it, wrapping in behind the low. So you get very strong temperature contrast, really good frontogenesis in here. So just a picture of applying what you're seeing this week, literally, to what you're learning about as well this week. So hope you got something from this, and please don't hesitate to ask if you have any questions.